So today we are going to be covering circuit analysis in the frequency domain. So I'm going to find a circuit to look at real quick, probably from an old Circuits 1 test, and then we will walk our way through that. Let's see. Dropbox 220. I'm having trouble finding a problem where I make students do stuff in the time domain first. Alrighty, this guy's fairly straightforward. So our circuit of interest will be this guy. All right, so we are going to avoid working this in the time domain because of the brutal amount of calculus that would be involved. So instead, we're going to look at this problem in the frequency domain. So the first thing that we're going to need to do is to convert all of our voltages and currents into phasor quantities, and then convert all of our resistors, capacitors, and inductors into their frequency dependent form, which is known as an impedance. So the phasor voltage Vs based on the waveform that I have described would be what?
-20 degrees.
That is correct. Oops, so that's easy enough. So I'm going to redraw my circuit. And I'm going to put 20 angle negative 20 degrees volts here. I'm going to have a phasor voltage VC here, a phasor current IL here. So all of my voltages and currents have now been converted to their phasor equivalent form. So now I need to figure out what the impedance of everything is going to be. So what's the impedance of a resistor?
You just leave it as is.
Right. So nothing wild or crazy there. And then the impedance of a capacitor, 1 over j omega c. So that would be 1 divided by j, what's omega?
100.
100 radians per second. Times c, which is 3 millifarads. That's going to give me negative 10 over 3 j ohms. And the impedance of an inductor is j omega L. So that'll be j times 100 per second times 16 millihenry. So that's 100 j times 16 times 10 to the minus 3. 1.6 j ohms. Alrighty, so we have converted from the time domain to the frequency domain. So now we need to figure out how to best determine our phasor voltage VC and our phasor current IL. Do you guys have any ideas?
I do, but it might not be the best.
Well, what you got?
So I would do a source transformation on the 20 angle negative 20, and I would combine the 2 ohm and the inductor and just do nodal.
So you're saying do a source transformation on the 20 angle negative 20 and the 5 ohm resistor, and then you would do nodal analysis. I would argue, so doing nodal analysis is fine, but with complex numbers, it effectively involves the use of a computer to do it directly. The calculators that we use in this class can't do it directly. We could do Kramer's rule. I'm typically not mean enough to make you guys do that, so I try to avoid setting up a system of equations if at all possible. Now, your idea of doing a source transformation, though, does have significant merit. And so let me explain why that would be. So if we do a source transformation, 20 over 5, so this is going to be 4 angle minus 20 degrees amps. In parallel with a 5 ohm resistor, in parallel with a minus j 10 over 3 ohm. Sorry, that should be a capacitor, not a resistor, but at this point it doesn't really matter, so I guess I could have left it. Here we have our inductance, and I'm going to do what you suggested there and combine those two inductances, or excuse me, those two impedances. So I'm going to use a generic circuit element, and I'm going to call this 2 plus j 1.6 ohms. So doing a source transformation, this is what we are left with, where this is our current IL, and this is our voltage VC. So we have a single node pair circuit now, which should be fairly easy to analyze. So we could, I wouldn't even really call it nodal analysis at this point, because there's only one node and then what would be your ground node. But we could apply Kirchhoff's current law at the top node and figure out what IL, let's see. So if we did KCL the top node and put everything in common terms of VC, we could have a one equation, one unknown system and solve for VC, and then use VC to solve for IL. We could alternatively do current division and solve for IL, and then we would know that IL times the impedance 2 plus J 1.6 ohms would be VC. So which route would you prefer?
I feel like current division might be shorter.
Okay. So applying, excuse me, the principle of current division, we could see that IL would be 4 angle negative 20 degrees amps. And then I'm going to have 1 over 5 ohms here, 1 over, all right, so this one's going to be awkward. 1 over negative J 10 thirds is going to be
Negative 3 over 10, J.
negative 3, yeah, over 10, J 10. But a negative J in the denominator, or excuse me, in the, yeah, a negative J in the denominator would look like a positive J in the numerator. I'll leave it as it is. That's probably too confusing. 2 plus J 1.6 ohms. And then 1 over 1.6 ohms goes here. Take a minute to throw that in my calculator. Not 16, 1.6. That was almost bad. I get 3.074 with an angle of negative 45 degrees. 3.074, yes. Actually, let me check something real quick. Okay, no, it should be minus 65 degrees. Amps. Insert should be minus 20. There we go. Double check it. Need to change the mode on my calculator because it's giving me everything in rectangular and it's just driving me nuts.
Dr. Hartman, quick question.
Yes, sir.
What calculator are you using?
TI 36X.
Okay, awesome. Thank you.
And I put the expression into my calculator effectively exactly as it's written here. All right, so that is our current IL. Now, VC is simply IL times 2 plus J 1.6 ohms, just using Ohm's law, right? Because if all of these elements are in parallel, then if we know the voltage drop over that rightmost branch, we know the voltage drop over everything. .874 angle negative 26.340 degrees. So these are our phasor domain relationships. How would we get our time domain?
So we have the magnitude for both, and the frequency would be the same. And all we need to do is add those angles, right?
Yeah, so we would have 3.074 cosine omega was 100 t minus 65 degrees amps, and VC of t would be 7.874 cosine 100 t minus 26.340 degrees volts. So I'm going to scroll back up here and look at this. So that was a pretty, in my mind, a pretty efficient way to go through the problem. So I commend you for suggesting the source transformation, because that is not where my mind immediately went. Where my mind went originally was to do voltage division to determine VC, and then use Ohm's law once we know VC to determine IL. I think it's the same amount of steps, and some of the math is going to be extraordinarily similar. So whatever way really floats your boat here. I guess another thing that we could have done as well is if we combine these two and assume our reference to be here, this node has the only unknown voltage, because our other node has a known voltage with respect to ground. And so we could set up a simple one equation, one unknown, which we could algebraically solve to get VC, and then use VC to determine IL using Ohm's law again. So there's multiple different ways that we're going to be able to approach practically every problem that I give you in the steady state sinusoidal section of our class. And that goes the same actually for the three-phase section too. It just depends. It's really about employing whatever circuit analysis techniques you're comfortable with to eliminate careless mistakes. Because a simple mistake here of fat fingering a wrong key and messing up a phase angle or something like that will propagate through the whole problem. The analysis that we're doing is the exact same as what was done in DC circuit analysis, but because we have these complex numbers that we have to pay attention to, where some of them are going to have positive J's and others are going to have negative J's, we're going to have phase angles that we got to worry about. There's just a lot of opportunity to make very simple mathematical errors. And that's where the bulk of the mistakes are going to come from. It's not going to be from applying circuit analysis. It's going to be from bookkeeping. All right, so let's see. Let's work one more example, and then I think we'll wrap it up for the day. So this problem just starts off in the frequency domain. Goal here is to determine the Thevenin equivalent impedance of this circuit. So how would we go about doing that? We have two different routes we can take.
It's going to be a test source method, right?
So we could use the test source method to solve for it directly. That is correct. We could also, because we have a independent voltage source here, we could also find V Thevenin and I Norton and then take the ratio of those two. That's on the table because of this independent source. So which route would you guys prefer to go?
I'd like to try the Thevenin I Norton stuff. If anybody else wants to do something different, that's fine.
Well, you're the only one talking, so let's go for it. All right, so the Thevenin equivalent voltage then. So that means that we're trying to find, I'm assuming positive polarity on top. So the Thevenin equivalent phasor voltage would be there. All right, so how would you suggest we go about doing this? Because I've actually solved it in my head already.
I personally am not sure because I didn't even know you could do it this way. I thought you had to do the test source method for stuff like this.
Nope, absolutely not. All right, so let me ask you gentlemen a question. What is Vx?
The voltage drop across impedance.
Right, but what is its numerical value? We can determine that just by looking at the circuit. How much current is flowing through the J4 ohm resistor or inductor?
None.
Oh, none?
So what's the voltage drop over the J4 ohm inductor?
0.
Okay, so if the voltage drop over if Vx is 0, then how much current is being supplied by that dependent source?
None.
Right, so if no current is being supplied by the dependent source, it's supplying 0 amps. What does a 0 amp current source look like?
It's just an open circuit.
An open circuit. So we could redraw this guy. It's not really necessary, but let me do it. This Vx we know to be 0, but that's, I'm still just going to draw it. So what's V Thevenin have to be?
3 angle 30.
Yep. I said I did it in my head. Just using that exact thought process. Well, if Vx is 0, and it has to be, then that means that that current source really is behaving as if it were an open circuit. So this 3 angle 30 here is the same as this 3 angle 30 here because there's no voltage drop over any of our impedances. So that one, fairly straightforward. Our Norton current, maybe a little bit more difficult. Let's just revisit this guy up here and see what's up. So this is our phasor Norton current. I've shorted out our terminals and I'm finding the current direction down. So how could we go about doing this or determining this?
Could you do source transformation like on the last problem and then current division?
The problem with doing current division there is that we don't have that dependent source. We can't just treat it as a impedance in parallel with everything else because it's not an impedance. So it's going to require a little bit more work than that.
Just gonna have to do mesh to it then?
So I'm trying to avoid doing mesh because mesh means that I would have to do Kramer's rule to solve it, Kramer's rule or MathCAD. So here's what I think I'm going to do. Yeah. So I'm doing nodal analysis, but I only have one node. And this nodal voltage is the exact same thing as the phasor voltage Vx. As I've drawn the circuit, right? The left-hand terminal is, this node is associated with the positive polarity terminal, and then ground is associated with the negative polarity terminal. So Vx is effectively describing a nodal voltage if I choose my reference node to be the bottom. So I could say that Vx minus 3 angle 30 degrees volts divided by negative J 0.5 ohms. So that's the current directed to the left through the capacitor, plus 0.5 Vx, that's the current directed down, plus Vx divided by J4 ohms is equal to 0. And so what that lets me do, I think I'm running out of room on this page, so I'll have to sneak it over here. So if I factor out Vx, I'm going to have 1 over minus J 0.5 ohms plus 0.5 plus 1 over J4 ohms is equal to 3 angle 30 degrees volts divided by negative J 0.5 ohms, if I did my algebra correctly. So let me make sure that I did my algebra correctly. So I took this guy, factored out Vx, this guy factored out Vx, this guy factored out Vx. It looks like all my signs are correct. I moved this guy over to the right-hand side, and in doing that, I had to move the whole fractional form. So yeah. So this negative sign here got canceled out when I moved things over, and I'm retaining that one. All right, so that, excuse me, that is something that I can actually just solve using my calculator, right? Because if I take 3 angle 30 degrees and divide that by negative 0.5 J, I get 6 angle 120 degrees. And that would be amps. I can divide that 6 angle 120 degrees amps by this form, and that will leave me with Vx. So that divided by -1 over 0.5 J plus 0.5 plus 1 over 4J gives me 3.297 angle 45.945 degrees volts. And coming back over here, now that I know what Vx is, what's I Norton going to be?
Norton's going to be the Vx divided by the J4 impedance.
Yep, that's exactly right. Vx over J4 ohms. .824 angle negative 44.054 no 055 degrees amps. All right, so our Thevenin impedance will then be our Thevenin voltage divided by our Norton current. So let me store that. So that is 3 angle 30 degrees divided by this 0.824 business gives me 3.640 angle 74.055 degrees ohms, or if you prefer rectangular coordinates, 1 plus J 3.5. And we could, if we wanted to, go through and verify that by using a test source analysis. It's up to you guys if we bother with it.
Nah, I don't think I want to see that.
Yeah, I trust your answer.
Okay. Well, does any of the analysis that I've done here not make sense? Let's start there.
Looks good to me.
Yeah, I mean, I'm just applying the basic DC steady state circuit analysis tools that we used for, you know, gosh, the first month and a half of Circuits 1, and applying it in these sinusoidal steady state problems where I can treat everything as a DC circuit as long as I'm using the phasor domain stuff. So impedances or admittances, but 99.9% of the time impedances, as well as, you know, phasor relationships for voltages and current and such. All right, so if you guys don't have any questions, you know, this hopefully was just pretty much review. What we're going to cover on Thursday will be, I believe, analyzing multi-frequency circuits. So I'll try to come up with a reasonably ugly looking problem that we can fumble our way through. That'll be much more difficult than the one I gave you on your homework, and hopefully clear up any questions you might have there. So unless anybody has anything else, I'll see you guys on Thursday.
Dr. Hartman, I got a quick question.
Yes, sir.
For homework 11, the first problem was asking like leading, lagging terms, stuff like that. Is there an easy way to figure out which one is leading, which one's lagging?
Yes. Go to my YouTube channel and look up my sinusoidal review lecture thingy. And there's a section on leading and lagging that should make it incredibly simple for you to figure out how to do it.
Awesome, thank you.
Yep. Any other questions? All right. Well, I'll catch you guys on Thursday. Have a good rest of your day.